Excellent. Well, our next talk today, we have Jason Cantarella, who is a professor of mathematics at the University of Georgia with research in the general area of geometric knot theory. His research focuses on shapes of random curves and polygons, and he's particularly interested in questions like how likely is it that a random curve is knotted, or what can we expect from a random diagram of a random space curve. He also writes software to experiment with and illustrate mathematics for teaching and research applications, including games. I was recently playing a fun one called Calculus Wars on his website. So I'm excited to hear from Jason.
All right. Well, thank you very much. It's really fun to come. I had no idea what the audience would be for this talk, so I prepared a super non-technical talk, and I was like, I'm going to put as few words on my slides as possible, which means that if you have a technical question, you should just ask in the chat or something. I can't do Discord and speak at the same time, and I'd be happy to stop and say more. But let me start by, we start here. I'll share my screen. And all right, does everybody see it? Okay, so we're going to talk about new ways to find and visualize knot isotopies. So there's one as an example. So we'll come back to it at the end of the talk, but I wanted to pick up my Borromean rings. And this is something that dates from, I don't know, when Aaron was at the University of Georgia. And we made these vacuum cleaner knots, and we used to play with them in my office back in the day. And one of the things we noticed was that if you take these Borromean rings, there's this like weird thing you can do with it where you kind of turn them inside out. And we're like, oh, that's funny. It's like some isotopy in the configuration space of the Borromean rings. And somewhere in the middle, there's this like weird unstable configuration of the Borromean rings that's kind of flat. So this stuck with me for a long time because I was like, does that mean there's like a, pi one in the configuration space of the Borromean rings? Ryan Budney, I think, proved that the answer is yes. And of course, being in geometry, I was like, well, does that mean there's like a closed geodesic in the configuration space of the Borromean rings? Like, is there some optimal way to do this loop? And so that's the picture I'm sharing. Yes, there is. So let me build up to that over a series of other projects that are basically visual. So here's a question, right? Is it a knot? So you can look at this thing and you can imagine like things you might do with it. So I don't know if you can raise your hand in the video or something, but does everyone see something they could do? Okay, Aaron's nodding. I see some nods. So I think one thing that you can do with this is there's this loop on the left-hand side that goes under everything else. And you could kind of imagine like, well, I'm going to pull that under the whole thing and then hope that things get better after that. So what about this one? Not or not? Anyone want to vote? I should figure out how to take a Zoom poll, but I won't do it right now. So think to yourself what you think about it. It's really not obvious what you might do with it, right? I don't see any obvious moves for this one. And then there's this one, same problem. This one is a classic. You can kind of see what's going on there. Somebody folded some rope in half, tied trefoils in the ends and then brought the loops back over the trefoils in the middle. So at least you have a sense for what you might do to unknot it. You pull the little loops off and feed them around the trefoils, and then you could kind of slither the whole thing back through itself. This one's just hard. At this point, I start to lose track of what's even going on. This is the famous Okai knot. And this is a whitehead double of a whitehead double of a whitehead double of the first knot we saw, actually. Yeah. So actually, all these are unknots. And these are famous examples of hard unknots. And they're hard for people. And they're hard for computers too. So, if you want to undo it, here's a way to undo the first one. It's called the culprit. And you can see that the picture on the right takes some close study to understand what's going on. But it basically starts with the idea that you're going to pull that thing on the left around back and loop it over the whole thing, and then things will start happening and you'll see what to do next when you get there. So this is a lot like solving a maze. And one of the things that I thought when I was looking at this is, solving a maze is one of those classical topology problems where you're like, but there aren't any mazes, right? The walls are contractible. So there can't really be any complication here. Like there's some path in R2 from one side to the other. So yeah, I know you want to do it, right? So I don't see the answer. But look now. Right? So here, the maze on the left, which I think is the same. Oh no, I put the wrong picture in. Okay, the maze on the left is hard. The maze on the right is easy. And all I did was color the two connected components of the walls different colors. This is a great exercise to do with small children because they really love coloring in the walls of the maze. More than they like solving the mazes themselves. But once you do that, it's sort of obvious what the answer is. So a question is, maybe you could do that to solve not mazes. Maybe color would really help. So here's something that is classical and also doesn't help. You can say, well, okay, there are 3 moves you can make, and everything can be expressed as a chain of these 3 moves, which means there's some sort of maze-like thing in which every picture is like a room in the maze, and there are various doors in the room that correspond to these 3 operations. And you could wander around choosing doors to go through and hope you get to something simpler. So the first 2, at least it's clear which way makes things simpler. The third one, of course, it's not. So you can get lost very quickly wandering around the maze by just doing random moves like this. So this is not useful computationally. But here's like a way to think of all these 3 things that turned out to be like surprisingly good. In each case, there's some stuff that goes over or under some other stuff, and you could push it aside. So this is called a pass move. Here's some examples of pass moves. So for instance, on the block in the middle on the top, there's what looks like a Reidemeister 1 move, this untwist. Of course, it's got stuff inside it, so it's not really a Reidemeister 1, but it really is like a loop that goes over everything else and comes back to itself. So you could redefine that twist move to be, oh, when I have a loop that goes over everything else and comes back to itself, I could just get rid of it. Then on the bottom of that same picture, you see something like uh, it's a little more like a Reidemeister 2, but maybe it's just the analogy starts to break. You've got this arc that goes under everything else, and it passes under two arcs of the diagram. But if I reroute it to the dotted line, it only goes under one arc. So that's better. Um, and you can do something similar in the picture on the top right, where you're like, okay, this heavily shaded arc goes under 1, 2, 3, 4, 5 arcs of the thing. But I could reroute it around the outside to go through only one. So it'd be a lot better to do that. Um, so this is the idea. The first idea then is to find these over and underpasses or these bridges and try to reroute them. Okay, so here's an example, right? Not or unnot. I already modified it so there aren't any reducing Reidemeister 1s or 2s. That would make the game too easy. Um, of course, there are lots of Reidemeister 3s, but how do you know which ones to do? Right? You could run out of computer time very quickly wandering around doing Reidemeister 3s and hoping to unlock something. So let's just try highlighting some of the overpasses. So there are two big, juicy looking overpasses right there, right, in blue. And here are two more. And you can see if you look at these things that maybe there's some hope of rerouting them so they would have fewer crossings. So here are reroutings for the first two. The first one, I think, crossed 4 times in its blue configuration, but if I flip it over to the orange loop, it only crosses once. And on the right-hand side, if I change from the blue loop to the orange path, I think it's 5 to 2 or something.
Downhill. It doesn't like running uphill.
So here's the same kind of thing. On the left one, you see it's 6 to 0, maybe. And on the right-hand one, it's like 3 to 2. So these kind of reroutings are actually surprisingly efficient as a way to simplify knot diagrams. And of course, like once you do some reroutings, maybe you'll unlock more reroutings that are visible to you now that you've moved stuff aside. So what is this really? The knot diagram has a dual graph, which I drew in, and maybe you guys have had this experience too. Like 3 days ago, I was like, it'd be really nice if I had a picture of the dual graph and the reroutings to show in my talk. And so I've been awake and coding more or less consistently since I had that thought. And I finished this, sometime like midnight last night or something. when I was like, see, I can produce automated layouts of the dual graph, which look nice. So appreciate, the picture on the right. And you can see it's not so obvious from that picture how the rerouting at the left works, but it is indeed a path of length sort of 0 in the, or maybe in the dual graph, where you see that the two arcs you had originally are part of the same face. So in fact, you can just go across that face and not introduce any new crossings at all. Okay, but it can always get worse, right? Yeah. So here are two more pictures. And okay, one of them is a knot and one of them isn't. um, and I will stipulate that neither of them has any improving pass moves, right? So the one at the right was found by this Oxford DeepMind team that was trying to train an AI to untangle knots. And their thing just died at this point. So they published a paper with, here's like a gigabyte of diagrams we couldn't do anything with. Go for it. So this is one of their very hard examples. And the one on the left happened to me organically. I was doing some experiments with self-avoiding walks and trying to classify the knot type of closed self-avoiding walks. And I got this diagram that I couldn't classify. And I was like, well, wait, I mean, I can do its Jones polynomial, like I know what knot it is. It's two trefoils, but why can't I simplify it to two trefoils with, pass moves or something? And the answer is there aren't any pass moves here, because the thing that you would have to do, has everyone seen it yet? Is move a strand that's between some other stuff. So the vertical strand that's longest is over 3 things and under 1. And if you slide it under the arc that it's under at the bottom to the left, you can route it around the loop going under it. It's kind of like a Reidemeister 2. And you can switch from 3 crossings of the thing underneath to 1 crossing of the thing underneath. And when you do, you'll reveal this as a connect sum of 2 trefoils. Okay, so there's a little picture of connect sums, right? So in this connect sum, this thing is diagrammatically composite, right? Which means that like in the diagram, you can separate the 2 pieces. So if you think about that from the point of view of the dual graph, this is like a loop of length 2 in the dual graph. You start at this face in the middle where the bridge is, then you go to the outside face, then you go back to the bridge face from the other side, and you've crossed 2 edges to do it. But of course, neither of these pictures, and in particular the one on the left, is not diagrammatically composite. So here's a new idea. Diagrams can be vertically composite without being diagrammatically composite. So you just have to stare at these two for a minute to understand what vertically composite means. But do you see it? The blue half of the curve always goes over the red half, even though red and blue crossings could go either way. All the red-blue crossings have blue over red. And that means that if you think about it, you could slide a plane through the middle of this diagram, which blocked out all the red stuff. and separated the red stuff and the blue stuff. So these really are composite diagrams. They're just not composite as graphs. You have to take the crossing information into account too. So of course, on the left one, it's sort of obvious once you make the slice that they're both trefoils. On the right one, it's not instantly obvious that they're both unknots, although they are. But at least you can see that if you connect the two ends of the blue thing, you can immediately do an untwisting there, and then you can pull that loop underneath the next thing, which gives you some hope that, then you're like off to the races. And it turns out that with a combination of pass moves, well, all the Reidemeister moves are pass moves. So I'll just say, by doing enough pass moves, you can go through reducing pass moves that get the blue and the red component down to zero crossing diagrams very quickly. So, okay, but what's really going on here? So I should say that the Oxford DeepMind team came up with 384 really hard unknots. And it turns out that about half of them are vertical connect sums, which means half of them aren't vertical connect sums, which means we have to defeat them. So here's another idea, right? What the crossing information is telling you about knots is it's like a partial ordering, right? If I see an arc of the thing going over another arc, there's some combinatorial object in which something is greater than something else. And maybe two arcs don't touch each other, so they're just not comparable. So you could imagine some strategy where you're going to start somewhere on the knot and you're going to walk around and you're going to stay level. Everybody else is going to get out of your way. And you'll have to stop doing that when you get back to yourself. So do that. Now, when you get back to yourself, you're either going over or under, but either way, start a new color, right? And that color will stay level until one of two things happens. It arrives at itself or it arrives at the first colored arc. Now, if it arrives at the first time it arrives at the first colored arc, it's going over or under. But that's the relationship between the two. Once it chooses, it has to stay the same relation under or over at all future encounters with that previous arc. Well, okay, so you continue until you have to stop. And by doing so, you can sort of break the diagram up into different pieces, all of which are allowed to be at the same level, but which have some ordering relationship with respect to each other. If you're careful about this, you can make this partial ordering transitive, though you have to do things like keep track of all the colors you're below. And if you pass under somebody else, all of their overcolors become your overcolors. And all of your undercolors become their undercolors. So you break it up more often than you might think. But the diagram at the right is one such breakup. And the rule is then that each of these arcs is, okay, so if you extended this partial ordering to a total ordering, that would separate the diagram into like a stack of transparencies, right, that are put down over one another. And there's some verticals you don't see. And then each of these arcs can be rerouted within its own level, as long as you avoid the vertical punctures. So here's an example, which tells you that sometimes changing your perspective is the key to solving a problem. So this picture at the left is the same thing, but I extended to a total order and put all the arcs at their heights from the total order. And on the right, I just rotated that so you can see that combinatorial data really does give you a way to reconstruct like 3D geometry. It's not unique, but this is a way to construct 3D geometry. And of course, once you rotate it, you can start to see all kinds of pass moves and other things that you can do to the diagram on the right. So you could rotate and reproject, re-embedding. Gives you a new diagram drastically different from your old diagram, which is guaranteed to be the same knot. All right, so here's an example at left of the same knot from one of our experiments where we extended to a total ordering in a geometric way by solving a constrained variational problem. We were trying to minimize the total variation of the height function, which turns out to be a nice thing to do because it preserves this broad structure. And that step is super fast. And on the right-hand side, you see the same embedding, but I just smoothed it out a little and made a nice like Havre picture with shadows and stuff because that was cool. Okay, so why did we do this? Because we had like these random knot experiments where we were regularly generating diagrams with tens of thousands and then hundreds of thousands and then millions of crossings. And the knots themselves weren't all that complicated, but the diagrams were horrible. So we needed some very, very fast way to simplify diagrams. SnapPy will do pass moves in Python, but it's comparatively very slow. So here is an example from the kind of thing we run in bulk. There's some 10,000 edge random polygon, and when you project it, it's this 14,000 crossing diagram. But when you simplify it, it's only a 205 crossing knot, which has a lot of connected components, most of which are trefoils. And the most complicated one is this 40 crossing thing in the top left. And then you can compute the Hamfly polynomial really quickly. So, there you can do the, exponentially hard Hamfly polynomial or the Jones polynomial for a 14,000 crossing thing, in 100 milliseconds. Okay, but this is the illustrating math seminar, not the like random knot seminar. So I will ask the question that is really on everyone's mind, which is, yeah, but can you animate these moves? Because that would be really cool. So on the right, I have a video. Okay, so let's watch that again. Because man, I worked really hard on it. So this thing is done by my collaborator, Henrik Schumacher, who is a numerical genius among being many other kinds of genius. And this is a new algorithm for minimizing repulsive energy called the tangent point energy. It's numerically extremely hard to do. But this is a new fast code for doing it. Unlike the other things, which were like, 100 milliseconds or 5 milliseconds, this takes about 30 or 40 seconds to do the minimization and a lot longer to render it. Well, actually, it's not longer to render it. It's longer to do it though. But it does succeed at unknotting it. Which is really satisfying. Okay, now, but of course, like you can never stop when you're ahead. So you're like, well, that's kind of a cool animation, but is it the best possible animation? Well, okay, like here's a classical not isotopy problem. Prove that the figure eight is amphichiral by finding an isotopy between the figure eight and the mirror image of the figure eight. I can flow both figure eights to the same thing by energy minimization and get a path that goes from one to the other. But is it the best path? Um, well, the best path is the shortest in some metric. And here's a shortest path done by Schumacher and his collaborators in a metric they invented. So they both came up with a metric on embedded curves and came up with a metric where the non-embedded curves were sort of pushed off to infinity, so you would never go there. And then found a way to numerically find geodesics in this metric. And then they isotoped the path from the energy path from one figure eight to the other one to a geodesic by numerically minimizing the curve. So we're just going to watch it because it's awesome. So that, I think, is the best animation from the figure eight to its mirror image. And it is the best in some precise sense. You know, this is a geodesic from one to the other. Can I prove it's the minimizing geodesic? Of course not. Don't be unreasonable. But it's a short geodesic. And boy, it looks really cool, right? So of course, once you have the capability of doing this, you want to try other stuff. So here's another one that's a classic, right? The one on the right is a picture of Henry Siegerman, I think, about finding an isotopy from the trefoil to itself from the 2-3 torus knot version of the trefoil to the 3-2 torus knot version. So on the left, you see the 2-3 in my picture. I think that's the red one in Henry's picture. And then the blue one in Henry's picture is the 3-2. And you can get from one to the other in the 3 sphere by morphing the tori to one another through the Clifford torus in the middle. Or you could do this geodesic thing. And the geodesic thing is really pleasurable. It does not have any of the geometry associated with the 3 sphere or stereographic projection or anything. I have no theoretical explanation for it. But it's a really satisfying picture. Which of course brings us back to the Borromean rings. Because when Henrik came to me and said, we can do these geodesics, I was like, well, have you found any closed geodesics? And he said, no, where would I even look for one? Like I could loop the 3-2 to 2-3 thing, but are there any closed geodesics? And I said, well, I know a closed geodesic in a curved space, or at least I think I do. And it turns out that this is indeed a closed geodesic. So I'll show you one version. And another version. These are in somewhat different metrics on the curve space, but I think they're kind of equally hypnotic. And indeed, like I can very happily sit here and watch them for a very long time. So I have no idea whether I'm ahead of or behind time. But in any case, that's my last slide. So thank you very much for inviting me. and I'm happy to discuss things or show more pictures if you like.
Thank you so much, Jason. That was amazing. Yeah, I figured I'd kick off the questions by just having some by mirror or bouncing something from the Discord from Henry Siegerman, who asked if there were any bounds for simplifying knots in this way, or if it was heuristics that always seemed to work.
Oh, that's such a good question, Henry. So, it's no, it's really like heuristics that seem to work. Um, you can imagine coming up with some proof that you know, everything is a vertical connect sum, but it's not, right? Not every unknot it either has a pass move or is a vertical connect sum. So what we have now is every hard unknot example that we can find, if you re-embed it with the energy, with the height, with the total variation energy and rotate it, and then do pass moves, it simplifies it. So we simplified all the examples that are known in the literature, Hawkins unknot and the Okai unknots and the unknots found by the Oxford DeepMind guys and the unknots found by Gukov and the Caltech guys and the unknots found by Adam Sikora when he was trying to disprove the Jones conjecture or maybe prove the Jones conjecture numerically. And so far, we haven't found anything that doesn't work. So I challenge you all, but in particular, Henry, because he's likely to actually be able to do it, to come up with a hard unknot example that fails this like energy rerouting and rotating test. Because honestly, it's going to be really hard to publish a paper on this if we say it seems to work for everything, because you sound sort of like a crank. So I would love to just have an example where it doesn't work before Lou referees it and spends like 9 months coming up with something. So beat it now, like save me the struggle. And you can send unknots to me in any form whatsoever, including like hand drawings and pictures of piles of string. I would love to hear them.
I want to open it up for other questions. It looks like there was one in the chat that asked, did Keenan Crane pioneer tangent point energy?
So Henrik worked with Keenan on the tangent point energy. Keenan didn't invent tangent point energies. That goes back probably to like John Maddox and Oscar Gonzalez, and even further back into the knot energy like mists of the past. But Keenan did some great work on numerics of tangent point energies, as well as tangent point energies for surfaces and so forth. And he has some really cool videos on this.
I had a couple of questions, Jason, if you don't mind.
Oh yeah, cool.
One is like, I suspect you've done this, but like, have you tried out your methods on those early knots produced by like Joel Haas and various people that first showed their large bounds on how many Reidemeister moves you might need?
Yeah, those bounds don't work for pass moves. So there are
Right.
small bounds on how many pass moves you need.
I see. Okay.
So yeah, we did try those.
Okay. Yeah, good. I figured. So, and then my other question is like you mentioned this 2-3-3-2 torus situation.
Mm-hmm.
And so my other questions about that, you said that like it doesn't like respect any of the S3 geometry or anything like that. Do you know like I mean, there's maybe no reason to expect it to respect that, but do you actually know that it doesn't? Like, what if you, like, is it possible to sort of drag the torus along around with it and see, does something happen to that torus? Is it possible? Do you know?
Oh, that's an interesting question. Um, uh, so no, I guess I don't know that it doesn't respect the S3 geometry. It doesn't look like it respects the S3 geometry. And I guess I don't have the Schumacher's curve metric isn't conformally invariant or
Yeah.
anything like that. So I don't imagine that you could just, pull it up to S3 and do the calculation there. But you could certainly put the torus around and, modify the tori. And that would be cool. They have some great work with Keenan about surface reconfigurations that like just won the prize at SIGGRAPH last year, where you can do the same thing but with surfaces. You can take, one configuration of like a t-shirt and then the t-shirt inside out and come up with a surface path from one to the other that respects embeddedness and has beautiful geometric properties, which is way harder than anything I'm talking about here, both numerically and theoretically.
Yeah, I guess that reminds me, there are relatively older videos of like turning the torus inside out, right?
Yeah, yeah, that's right. That's like a gradient of Wilmore energy or something, um, uh, which can be done much better with these new Sobolev gradient techniques that Crane and Schumacher and von der Mosel and everyone have pioneered for energies and the tangent point energy. Like it works much better for things like Wilmore energy or curve shortening as well. But I think that hasn't been explored as much yet.
Well, wonderful. Thanks so much. Gabriel, are we ready to sign off for the day?
Sure. Yeah, there are threads for all three of the talks today, hanging out on Discord and getting commented on, and so folks can continue to chat. But yeah, I think other than that, it'd be a great time to sign off.
Great. Well, thanks again, everybody. Thanks to all of our speakers, and we'll see you again next time.
All right.